In this demo, we're going to show QGen's ability to generate various sorts of source code, Ada code, C code, and so on. This is a normal view of a Simulink model. It has two subsystems. This one's a virtual subsystem. We see it's doing a simple kind of filtering. And then we have a more complex subsystem here, which is an atomic subsystem. Atomic subsystems actually show up in the generated code as separate source files, while the virtual subsystems are effectively inlined where they appear within the overall model. So this is the normal set of menus for the Simulink user interface, but there is one additional menu here, QGen, and it has two options: build, which is to generate source code, and verify, which is to run the QGen model verifier. In this demo, we're going to be illustrating the QGen source code generator, QGen code generator. So we'll use the build menu to do that. And it's a very simple menu. It lets us choose which language we want to generate, either Ada Spark or Misra C. And we can control various options for generating code. And we can determine how failures of the standard Misra checks, Misra subset checks, are handled. In this case, we're just going to do the default, which is to generate Ada code for the entire model. And we'll see that this takes only a short amount of time. And down at the bottom here, we can see that it's taking various steps. And now we're completed. And if we look over in our set of source files, here's the model that we had created. And it's generated a directory full of source code here. This is the actual Ada source code that's been generated. In addition, it's generated two files, one which is a dump of the contents of the MATLAB workspace in case there are any references to that from the generated code. And this is a dump of information that's gathered by actually running the simulation for a couple of steps to determine the order in which the evaluations happen in the simulation. That allows us to exactly match the same order in the generated code. So now if we look at some of the code, we can open it here in the Simulink MATLAB GUI. And we're just opening one of the files. This is the overall model. If we look here, we also see that there are separate source files for the PID subsystem. And we didn't actually drill into the PID subsystem enough to notice that there was an atomic subsystem within that. But each atomic subsystem, be it nested or be it at the top level, will generate its own source file, as will the overall model. And here we can now look at the code generated from the overall model. And we see these comments which can determine where in the model this code is coming from. One of the subsystems was a virtual subsystem, and therefore code from the virtual subsystem will be included directly in the code for the overall model. And we can see here that this piece of Ada code here is derived from the KF block within the filter virtual subsystem within the controller for a model, the unit delay block, the sum2 block, the PV, and the sum1 block. So we've combined the code for all of these blocks within the filter and also this PV block, which was at the top level, and generated this one piece of Ada code. And this is the indicator that this is the end of all the Ada code associated with those blocks. Then we have another set of blocks which generate this one line of Ada code. And then again, we have another loop that's generated associated with this block. If we go over and look at the actual model, we can verify what we're seeing here. So here we have we're generating code for this model as a whole. And this is an atomic subsystem, so it will have its own source code here in PID. But we are inlining effectively the code associated with this set of Simulink blocks into the code we generate for this model as a whole. And so if we look at PID, for example, we will see the code for the PID subsystem. And if we drill into the PID subsystem here on the GUI, we'll see that it has quite a number of blocks, and it has within it yet another atomic subsystem, which is a relatively simple filter again. And actually, I'm sorry, it's a derivator. So if we look at the code for the PID subsystem, we can bring that up in this GUI. And again, we'll see the various traceability links here, which show us that this piece of code is all from the PID unit delay block. This piece of code is from this another unit delay block, unit delay 1. And here we have the code that effectively comes from the derivator. In any given subsystem, there's three sorts of code that's generated. There is the code generated to initialize the subsystem. This is the init states procedure. There's code that represents the computation performed by the subsystem. And then finally, if the subsystem has any local state, there is a procedure which updates the local state. And these three procedures effectively define or represent the subsystem in the generated source code. If there are nested subsystems, then you will see those nested subsystems operations, such as the derivator update, being called from within the enclosing subsystems operation. So there we see the derivator update. And if we go back to the init states, we saw a call in the derivator init states, and here at the bottom of comp, we should see a call on the derivator comp routine. It must have been elsewhere. Oh, there it is. The derivator comp procedure is called, and it's producing an out parameter here, which is then used at this point here. It's a matrix. Okay, so, and if we go into the derivator itself, we'll now see the lowest level subsystem, which won't be invoking any other subsystems operations. Here we have the init states, initializes the memory local to the derivator subsystem. Here we have the computation procedure, and finally we have the update procedure, which updates the memory associated with the derivator subsystem. Each unit delay has its own memory. That's so that we can effectively delay the value of a signal by 1 unit through the process of storing it and then retrieving it and sending it out. Okay, so that's the basic, that's the default code generation strategy. A couple of things to notice about it were that it combined multiple blocks into a single piece of generated code. It inlined various virtual subsystems, but it did not inline various atomic subsystems. So we're now going to exit or delete this code. So I'm going to delete this thing, as well as, we didn't actually look at these two files, the workspace dump and the types dump. We can do that. They're not terribly interesting to read, but they essentially record. The types file records the types of the inputs and the outputs to every block. This is useful when we're generating source code. This information is not explicit in the model. It's determined by Simulink when it starts executing or simulating a model. We run the model for one simulation round to gather this information. In addition, the workspace might have important variables. In this case, the workspace is effectively empty. So we can delete both of these files and do that now, just so that we can see that they are regenerated when we rerun the source code generation. Okay, so now if we go back to our window, which had the controller, and let's bring it back into the front and center here, and we can go back to the overall model. And at this point, we can redo our code generation, but this time let's change it. Let's generate C instead of Ada. Let's inline all of the subsystems instead of just the virtual subsystem. And we'll generate, well, let's just do that. I think that by itself will be interesting. So we should, instead of getting multiple source files, we should get just a single source file for the entire model. This can provide more efficient code in certain circumstances. It does have other downsides in terms of modularity and so on, but in some circumstances, that's what we want to do. So we'll do that for this particular example, just to show you the flexibility of the code generation. So now we're generating source code, and it should be showing up over here on the left. And in this case, we've chosen to generate C, and we've chosen to inline everything. So now if we look at the source, the file of source code, notice it's now C code, and there's only one source file that corresponds to the model. This other set of files, these are standard types that are used by every model. We can look in there if you'd like. We take a quick look inside. We can see that this is a set of standard types, things like Booleans and some functions to convert to and from Boolean and so on. They're just sort of an augment to the set of types that come with the typical C system. And here is the fully flattened, fully inlined, if you will, source code for, now in this case C, for the same model. And now we have, as before, we have the filter being inlined, but we can also now have the various code from the PID, which was a separate subsystem before. We saw there was a call on the init states procedure before. That's now disappeared. We've fully inlined all of the code for initializing in this case, or for computing. The comp procedure is the one that computes the value on each iteration produced by this model, all the different values of the signals and so on. And again, this is fully flattened, so we won't see any calls on any atomic subsystems here because they've all been inlined into this. And I guess when we're doing fully inlined, there's no reason to have a separate update operation, so we just inline the update within the overall computation. Okay, so that's a second example of how we generate code. And we'll again clean up the file here just so that we can tell when we've got new code. And we'll get rid of these two things. And we'll go back to our window containing the controller. And now we're going to generate code in a different way. We're going to create what is considered reusable code. What does that mean? That means code where if you happen to have the same subsystem used in more than one place, instead of creating multiple versions of that subsystem, it will share the code between them. Now, we don't have any examples of that here, that we only have one instance of each subsystem. But if we had multiple instances, the reusable code alternative would allow us to reduce the total amount of source code because we wouldn't be creating separate copies of source code for each instance of a given block. Now, how do we do that? Well, we have to now pass in more parameters to the generated code for a block instead of using global variables, which is the default mechanism for representing the state of a block. We now go to having local variables which are passed as parameters into the block. So let's now generate the code for this same procedure. We'll stick with C, but now instead of inlining, we want to do almost the opposite. We're going to generate reusable code, and we're going to wrap all of the input-output port data into structs or records if you're looking at C. So let's generate the code again now, and we'll take a look at what it generates. We will now expect to see multiple C source files, and let's see if that's true. sure enough, we've now got a C source file for the controller, for the derivator, for the PID. We've also got some files which define the various types that are going to be passed around. And now if we look at the code, let's say controller 4.c, if we look in there, we should begin to see some local data, which is used when we call the nested subsystem code. And here we have some local data instead of using globals. And when we find the call in the nested subsystem, here we go. We're calling the PID computation procedure. And we're now passing in its memory as well as structs for the input and output signals. So this code for PID comp could now be reused in multiple places within the model, and we wouldn't have to generate a separate instance of that code because now it's being given as parameters the data, the input signals, the output signals, as well as the state memory that it needs. And if we dig into the PID source code, we'll see now that the computation procedure has a parameter for the input, a parameter for the output, and a parameter for the state. And now we have the code, and it's now manipulating these input vectors and output vectors and so on. In this case, the input vector is called input, the output vector is called output, and so on. So we see it, instead of manipulating global variables, it's now manipulating parameters. Here it is calling another nested subsystem, again passing parameters in as well as memory needed for the subsystem and so on. And we'll see the same thing happens down here when we get to the update procedure. It would be calling the nested subsystem, passing it some memory to be updated. The update procedure only manipulates the state, it updates the state, whereas the computation does not update the state, but it uses the state to produce the output values on the output signals. Okay, and as one final example, let's do this for Ada so we can see the distinction here. We'll get rid of this code again. Obviously, you don't normally need to do this because aren't necessarily generating code in multiple ways for a single model, but just for the purposes of this demo, we're going to do that. Okay, so here we have the model again, and in this case, we're going to do essentially exactly the same thing we did before, but instead of generating C, we're going to generate Ada. And here we go. So now we should expect to see that we have a new directory full of code. In this case, it's Ada code, largely structured the same way. We have the controller, the nested PID subsystem, atomic subsystem, the nested derivator subsystem. And if we look at the PID subsystem again, we should see that it's now taking parameters for its procedure comp. Sure enough, the input parameter and the output parameter and some state, and it is passing, it is calling the nested derivator subsystem again with parameters and state. And here we're using the parameters rather than global variables to refer to the input signals as well as produce the output signals and so on. So only difference between this and the prior one is this is Ada as opposed to C. Okay, so that's illustrated the various ways that QGen can be used to generate code. Thank you very much.